All right, series example 3. This thing converges if and only if this thing converges. All right. If you're taking discrete math, or you're going to take discrete math, this if and only if, this is the double arrow or equivalent. Equivalence, meaning that if this is true, then that's true, and if that's true, then this is true. Then by the contrapositive, diverges if and only if diverges. Now, if you're not taking discrete math, or you're not going to take discrete math, you don't understand what I'm doing there, no big deal. Just remember that this goes both ways. If this converges, then that converges. If that converges, then that converges. Same thing with divergence. Diverges, 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 diverges. If you're, most of the situations you're probably going to deal with is you're concerned about convergence or divergence here, and you look at this to tell you what's going on here. All right. Okay, so that means we're going to look at this integral, this improper integral. Okay, we're going to write this as a finite integral. Let's see, we're going to write this as the integral from 1 to r, 1 over x dx. This is ln x from 1 to r, which is ln r minus ln 1. Remember, ln 1 is 0, so this is ln r. So that tells us that this is the limit as r approaches infinity of ln r. Okay. Now, if you look at the graph of ln, you'll see that it's always increasing, even though it is the slowest increasing function we can find. But in any case, it's still growing, it's still increasing. So as x approaches infinity, ln x approaches infinity. Or I guess in this case we have r's here. Okay, so as r approaches infinity, ln r approaches infinity. Really slow, but still infinity. All right, so because this equals infinity, we know that all right. Now just a word about equaling infinity. This infinity is just a symbol. All right, it doesn't actually equal anything. It just means that it increases without bound. We have no way of understanding its value. Okay.